There was a moment in physics where the equations were clean, the math worked, and scientists felt confident they understood how energy and light behaved. Then they ran the numbers on something as simple as a glowing hot object. The answer came back: infinite energy. Not a lot of energy. Infinite. Physics said the universe should have been flooding itself with endless radiation at every moment. So why wasn't it? And why did fixing that one weird answer end up breaking every assumption about reality you could think of? It all started with something as ordinary as a piece of metal sitting in a fire. Picture a metal poker sitting in a fireplace. As it heats up, it glows red, then shifts to orange, then burns white. And physicists in the late 1800s watched this happen and nodded because they had equations that explained it. Those equations came from the same classical mechanics that described how planets orbit and how steel bridges hold weight, so there wasn't any reason to question them. The equation they trusted most predicted how much energy a glowing object puts out at each color of light. Plug in the numbers for red light and orange light together, and you get sensible answers across both ends of that warm part of the spectrum, the kind of results that make you feel like the theory is solid. But then you move toward the blue end, toward shorter wavelengths, and into ultraviolet, and the equation stops giving sensible answers. It starts climbing. The predicted energy just keeps going up and up, with nothing to stop it. No ceiling, no limit, straight to infinity. Think about what that actually means for a second. Any warm object in the room, your coffee cup, your own body, the sidewalk sitting in sunlight, should be pumping out infinite radiation right now, according to that math. Every single object with any heat at all should be blasting out endless energy in every direction, and the universe should be completely unlivable. But you're sitting here fine, which tells you the equation wasn't just slightly off. It was broken in the most extreme way possible. Scientists named it the Ultraviolet Catastrophe, not because anything actually blew up, but because the theory fell apart completely right at the ultraviolet end of the spectrum. A small error in a theory is something you can fix with a tweak. An answer of infinity means the assumption underneath the whole thing is wrong, and classical physics had one assumption baked into everything: energy flows continuously, like water from a tap, in any amount, smooth and unbroken. That assumption had never caused problems before, so nobody thought to question it. Most physicists figured someone would sort it out eventually. Max Planck sat down to do exactly that, and he didn't start with a new theory. He started with the experimental data, the actual measurements of how glowing objects behaved, and worked backward to find an equation that fit. The only equation that worked required something strange. Energy couldn't flow in any amount. It could only come in fixed chunks, specific little packets with no in-between allowed. Planck called them quanta. He described it later as an act of desperation, and that's not an exaggeration. To make the math work, Planck had to abandon his long-held belief that the second law of thermodynamics was an absolute law of nature, something he'd defended for years. He didn't think he'd found something real about the universe. He thought he'd found a useful mathematical trick, and he hoped someone smarter would come along and explain it away. Instead, the trick turned out to be the most accurate description of reality anyone had ever written down, and it didn't stop with glowing metal. Planck's quantum idea, at first, only covered how energy gets released from a glowing object. It was a rule about the source, not about the light traveling away from it. Once the light left, everyone still pictured it as a wave, spreading outward through space the way ripples move across water, and that picture had serious evidence behind it. Built up over decades, the wave model of light wasn't a guess or a placeholder. It explained how light bends around corners, how two beams can cancel each other out, how light can be polarized, and it predicted the exact speed light travels, which made it one of the most trusted frameworks in all of physics. One physicist in the 1800s wrapped all of that up in just 4 equations, and they were so clean and complete that a lot of physicists genuinely felt like the science of light was basically done. Then Einstein, in 1905, looked at a completely different experiment and said something that made people uncomfortable. He argued that Planck's chunks weren't just a quirk of how hot objects emit energy. Light itself travels in discrete packets, and each packet carries a fixed amount of energy tied to its frequency. We now call those packets photons. The experiment that backed this up is called the photoelectric effect. Shine light on certain metals, and electrons get knocked off the surface. The surprise was how those electrons behaved depending on the light you used. If light were purely a wave, then a brighter light source should knock off faster electrons, because more wave energy would be crashing into the surface. But that's not what happens. Brighter light knocks off more electrons, not faster ones. To get faster electrons, you need higher frequency light, bluer light. And it doesn't matter how dim that blue light is, because each individual blue light photon carries more energy than a red one. So a single blue photon can do what a flood of red photons can't. Below a certain frequency, no electrons come off at all, no matter how intense the light source gets. That makes no sense if light is a wave, but it makes complete sense if light arrives as individual packets, each one carrying a fixed amount of energy based on its frequency. A single photon either carries enough energy to knock an electron loose, or it doesn't. Throwing more low-frequency photons at the surface doesn't help. You need the right frequency, and that's particle behavior, not wave behavior. Einstein won the Nobel Prize for this, not for relativity, which catches a lot of people off guard. So light is a wave and a particle. The number connecting all of it is tiny. Planck's constant, h, is roughly 6.626 times 10 to the negative 34th joule seconds. And at the scale of a single atom, it's the only thing that matters, which is where the next problem was waiting, because atoms themselves were still a mess. The atom was the next thing that didn't add up. Physicists knew atoms had a dense, positively charged center tensor, with electrons somewhere around it, and the obvious picture was electrons circling the nucleus the way planets circle the sun. That picture felt reasonable until someone actually ran the physics on it. Classical electromagnetism says any charged particle moving in a curved path has to radiate energy, because the electron is constantly changing direction as it curves around the nucleus, which means it's accelerating, and an accelerating charge bleeds energy away the whole time. That's not an assumption anyone made up. It falls directly out of Maxwell's equations, the same ones that explained light so well. The math puts the whole collapse at a fraction of a nanosecond, after which the electron crashes into the nucleus and the atom stops existing. Every atom, all of them, instantly. This wasn't some edge case or theoretical footnote. Classical physics, the same framework that nailed planetary motion and bridge construction, pointed straight at the conclusion that matter itself couldn't hold together, and yet matter was sitting there being completely stable. The framework had nothing to say about why. Niels Bohr looked at this in the early 1910s and did something that took nerve. He borrowed Planck's quantization idea and applied it directly to the electron's orbit, not because any existing theory told him to, but because it was the only move that made atoms stable. Bohr said electrons don't orbit at whatever distance they like. They can only exist at specific, fixed distances from the nucleus, each one tied to a specific energy level, with nothing allowed in between. Planck had described these fixed units as something like the pennies of the atomic world, the smallest coin you can spend, and Bohr applied that same logic to where an electron is allowed to sit. An electron doesn't gradually drift from one orbit to another. It's at one level, and then it's at another, with no in-between and no travel time. That's what a quantum leap actually is, a genuinely discontinuous jump, not a slow slide. Bohr's model worked cleanly for hydrogen, a single electron around a single proton, though it ran into trouble with atoms that had more electrons. But the core insight held. The lowest allowed energy level is as far in as the electron can go, and it can't radiate past that point because there's no lower state waiting for it. When an electron drops from a higher level down to a lower one, the energy difference gets released as a single photon with a frequency exactly matching that gap. So different elements glow in different colors because they each have different sets of allowed energy levels. And because those gaps are unique to each element, the light they emit is unique too. Neon glows red, sodium burns yellow, copper turns a flame green. Each one is a fingerprint written in light. What Bohr's model couldn't answer was why those specific energy levels exist in the first place, and what's actually enforcing the rule that electrons live here, but not there. Classical physics didn't fail because the people doing it were careless. It hit a wall at the very small, where the smooth, continuous logic of everyday life just stops working. Planck found that wall trying to fix a radiation formula. Einstein found it in a beam of light hitting metal. And Bohr found it in the question of why you exist at all. At small enough scales, nature doesn't do gradual. It jumps. Bohr's model could predict those jumps, but it couldn't explain what actually enforced them. Why do electrons live at those specific levels and nowhere else? That answer requires treating electrons not as tiny orbiting planets, but as something without a fixed location. And that weirdness is the exact reason every atom in your body holds its shape instead of collapsing straight into its own nucleus.